You did not bore us with your Flora.
What should I say?
I honestly don't know
Yeah.
what you should say to that.
Lili, thanks so much for joining us today.
Thank you. Yeah.
It's absolutely great to have you here.
Thank you for having me.
We're excited to hear about your research, but before we do that, can you tell us, who are you?
Yeah, I'm Lili Mou, and I'm an assistant professor at the Department of Computing Science, University of Alberta. I'm also an Amy Fellow and a CFAR AI chair.
One thing we often start with in our interviews is, tell me about how you got started in AI.
Sure. So I started my PhD in 2012, and I was in the Software Engineering Institute. So at that moment, it was the starting of deep learning, all this kind of stuff. And it was a very natural idea if I can apply deep learning techniques to programming language processing. So I just tried it, and it worked pretty well. And I tried both deep learning for program analysis and also generation. But the problem is it was a new topic at that moment, and my first paper was not accepted until 1 year later. So I just applied my technique to natural language processing, and it worked very well as well. So my first paper was at NLP, and I just entered the natural language processing domain because both programming language and natural language are languages. So I just tried again, and I started doing my NLP research.
Yeah, it's cool that there's that crossover, and you're working on an unnatural language now,
Yeah.
not just a natural language. So I remember when deep learning first started being applied to natural language, and the innovations that were required in order to make it work, like the vectorization of meaning and then, putting words together. You were sort of there at that moment. You were working on programming languages, but you were able to take some of what you had learned from that and apply
Yes.
it to.
So there were some challenges. For example, programming languages are pretty structured. So you have the syntax tree, and it's very structured. So traditional NLP techniques may not work very well for programming languages. So I proposed a tree-based convolutional model that can capture the tree structural information of programming language. And then I applied it to natural language again, and it worked also very well. That's how I started my NLP research.
And so you were working on generative AI way back.
Yeah.
Before it was cool.
Yeah, so I started doing program generation, I guess, in 2016. And the technique is pretty similar to what we are doing right now. We just train a model autoregressively, predicting one token by another, and it can generate some programs. Right now, of course, we understand the model architectures are much advanced, and we have better training methods, but the general framework is pretty much the same.
And it's obviously been a really exciting time for that kind of work. So when you were starting off in that, did you have any idea like, oh, this is going to be a really big thing, or did you know?
Not really. I guess we just because my institute is software engineering, so it's very natural to apply some deep learning techniques to programs, and it worked well. So we believe it's very promising, and many other students in the lab continue doing program analysis. But I just left the field and I entered the NLP domain.
Yeah, cool. So tell us about your current work.
My current work is mostly about natural language processing and how to make large language models more efficient, because it has a lot of benefits. For example, for startup companies, they don't have the budget for building the big clusters, or they don't have data like collect tons of samples to train the models. So the question is, how can I make my language model more efficient? It's deployable on a small device. It requires less samples to train, and or maybe adapt to a new task, and it will have a huge impact. And also, it's more green than running a bigger model.
So I didn't know that when you say efficiency, you mean not just power consumption and total number of computations. You also mean the amount of data?
Yes, so there are different kind of efficiencies. For example, the time efficiency, how fast my model runs, and also maybe training sample efficiency, how many samples do I need to make my model perform reasonably well? And also, for example, memory efficiency. Although my model may not be faster than yours, I consume much less memory. So fitting to the same device, I can run a bigger model. So there are all kinds of efficiencies. I think I'm touching many of them in my research.
Yeah, that's really cool.
So when you say that it requires a lot of resources for these kind of models, for people who maybe aren't familiar with them in like an intimate way? Like when we talk about the skill, how much does it take?
Sure. So to put things into perspective, we can think of how much data we need, for example, to train my model.
Yeah.
So it's very typical for people to crawl the entire Wikipedia and just train a large language model. And that's still not enough. And
Oh,
some people claim that they try to crawl as much data as possible from the entire internet.
Mm.
And they are still feeling that they are short of data.
Mhm.
So we are
wow.
now having a data shortage problem.
That's like the first time I've ever heard the complaint that there's not
So
enough
not
on the internet.
Yeah.
Like
yeah.
that's wow. So you like even with all that available, still running into
Yeah,
to
so that's
limitations?
because the model is growing bigger and bigger,
Mm.
which requires more and more data. So that's why it's very important to have an efficient model that has fewer parameters and it requires less data to train.
That's something that you've been working on a lot. I know we wanted to get into your work on Flora, which has shown some pretty promising results when it comes to reducing that kind of footprint. So can you tell us a little bit about what Flora is and the work you've been doing there?
Yeah, Flora is our recent ICML paper published last year, and that's about reducing the memory footprint for large language model training. So usually when we train a large language model, we need to deploy the model on our GPU, for example, and we need to keep a couple of copies for the parameters. For example, you need to store the gradient information
Mhm.
and the past gradient information so that if it changes too fast, you can reduce the learning rate for that dimension. So that's why training a large language model requires a huge memory for GPU. And this is not easily doable on a, let's say, single server or a small machine. Our work is to reduce the memory for those the gradient information during training. And what we did is we do a low rank projection, meaning that we keep the most important information in the low dimensional space. So we can reduce the memory footprint to a large extent during training. And then we can train a bigger and bigger model given the small device.
So like instead of storing all of the gradients, you're sort of compressing that information down to something smaller.
Yes,
Yeah.
exactly. So what's interesting is that we have a random projection to the low dimensional space, meaning that the projection matrix does not need to be stored either.
Oh.
And it's super efficient because you only need a very small dimensional space.
Huh.
And what we find is that random matrices have rich structures.
Mhm.
So even if we just reduce the dimensions to a very small number, let's say 100, or maybe even smaller, let's say 8, 16, we can still keep the general structure of the high dimensional space, and it works very well.
Yeah, I remember learning about random projections in grad school and being just
Yeah,
blown away by how far you can get with random.
yeah.
Yeah.
So it's analogous to crumble a piece of paper, and you can see the wrinkles are pretty random,
Mhm.
but you can see a lot of structures like triangles or whatever there. So that's the basic idea of the random projection for reducing the memory footprint for large language model training.
Oh, that's a good visual. So you can think of in memory, Lili's coming in and crumpling the piece of paper
Yeah,
in
so
memory so it's smaller.
you still have the rich structure there. It doesn't lose much information.
Uh,
Oh, okay. It's just kind of in a different shape almost, ones that can pack more
Yeah.
in. Oh, that's interesting.
what are some other approaches in the area that you compare to in your work?
So we compared with traditional low rank adaptation,
Uh,
and we see that our approach with the random projection is more efficient than theirs
huh,
because you don't need to store how you project
right.
it. It's just random.
Uh-huh.
And the random numbers are generated by pseudo random generators in computers. It's a deterministic process. So I
Ah,
can replicate the
right.
random procedure with just a starting
Just
point.
just a seed.
Yes, that's
Yeah.
a random seed.
Oh, that's
So,
beautiful.
yeah, so that's why we can reduce the space to a very large extent.
Right.
And since we have fewer parameters, it works well when the training set is small because my model is less overfitting.
Mhm.
You don't have so many parameters to tune, and the model is less powerful, and it solves the overfitting problem.
Right. So it's sort of like regularization and efficiency altogether.
Exactly.
Yeah.
So actually, in our experiments, we not only achieve less memory, but also higher performance
Hmm.
than LoRa and other methods.
Oh, cool.
Yeah. And when we say like higher performance, what does that
Yeah, it really depends on the task. So we have tried many natural language processing tasks, including classification, generation. We also tried image. So some examples include machine translation. So you give me an input sentence, let's say in French, and we translate it to English. So the question is how well my translation go.
You're not only getting things to work, you don't need as much hardware, you don't need as much time, you don't need as much data, but it's also working better in some ways.
Yes,
Wow.
that's right.
And you're talking about machine translation. I know that's another area that you've worked on,
Yep.
specifically with teacher-student type of metaphors. Can you tell us about that?
That comes to another paper in AAAI 2025. That's about multi-teacher distillation for zero-shot translation. So the basic idea is we have so many languages in the world, and for the translation, the directions can be pretty much any language to any other language.
Right.
And we don't have the parallel data to train any pairs of languages. So what we did is zero-shot translation, meaning that if you tell me what is the source language, what is the target language, the language model can figure it out by itself. But of course, you can imagine the performance is not ideal because it's never trained during the training process.
So just to make it concrete, like you could train on English, French, and then do like French Swahili or something like this.
Yeah, so for example, your training data is usually English-centric. So you have Romanian to English. You also have English to Dutch, but you don't have Romanian to Dutch.
Okay.
But you can directly translate from Romanian to Dutch by zero shot. Just tell me the source language is Romanian and the target language is Dutch, and the model can do that by itself. An alternative way to do zero-shot translation is by pivoting translation. So you go to English, so you first translate Romanian to English, and then English to Dutch, then both directions are trained.
Yeah.
But it suffers from the error accumulation problem because you have two-step translation. We see previous work does not work very well because it's very noisy and you don't have the direct supervision. So what we did is to ensemble them together, meaning that we will utilize direct translation, pivot translation, including different pivoting directions. And each of them is noisy. But what if we put them together? It smooths out the noise and gives you higher performance.
So what are each of the teaching models trained to do?
If we directly do the ensemble, you can imagine that it's very slow. So what we did is we trained another model from these different directions. So we first ensemble them together, and we train a student model that learns from the ensemble output. And this way, my student model is much faster than the teacher model because you only need to translate once. You don't have to go through all the directions. And it outperforms each of the directions because now it smooths out the noise. It learns from different perspectives. So that is the multi-teacher distillation for zero-shot translation. What is more interesting is that we find multi-teacher distillation is better than distilling from different teachers individually. This is analogous to, let's say, a graduate student having multiple supervisors. It's best not to talk to the supervisors individually because they may give conflicting instructions, or maybe their opinions don't agree with each other, and the student is confused.
Yeah.
So it's best to ask the supervisors to reach a consensus. And once the consensus is reached, you just learn from the consensus, and that gives much better performance than learning from the teachers individually.
Right. You're not dealing with like contradictory information or different priority or thing like that.
And are you ensembling like at the word prediction level? Like how do you ensemble?
Yes. So the ensemble at this moment is at the word prediction. So basically, each teacher will give a vote at a time, and then you will take the majority. But there's a problem for naive voting because we have 50,000 words, let's say, in the vocabulary. And if you do a 0-1 voting, it doesn't work.
Yeah.
You have to consider the confidence of the teachers. So if some teachers pointing to the same word, but with lower confidence, but some other teachers pointing to a different word with a higher confidence, then you will prefer this direction because, they maybe just an educated guess. And then there's another problem for naive averaging of the probabilities because we have so many words and we have a lot of teachers and it's pretty noisy. So what we proposed is a bi-level search that we first truncate the tail of the teacher distribution.
Mhm.
So you just ignore teachers' predictions if they're not very confident.
Mhm.
And you just focus on the teacher's confident suggestions.
Mhm.
And that works much better than just naive averaging or naive voting.
Mm. Yeah, they do that right in generation too. What is it called? Top P? Like,
Yes,
yeah,
it's a top P sampling.
right.
So when you sample from a distribution, you don't want to sample the long tail bad words. You want to focus on the top several words.
Mhm.
And it's similar to here. We do a voting. We just vote on the top words
Right.
suggested by the teachers.
Yeah.
But what advantage does that approach give in your work?
In our result, we see that the distilled student is much more efficient than the teacher because the student is smaller. And also you don't have to go through different directions. So it's much more efficient. And also it achieves slightly better performance than the consensus of the teachers.
Okay, so it's not only taking that consensus, but it's improving on it in some way.
Yes. So it improves the individual teachers to a large extent, but it's also better than the consensus of the teachers.
Why? What are you doing on top of it to give it that extra
You
boost?
just learn a student model. The student model, like my students, oftentimes outperform me.
You're training to use that information, but not copy it, I guess. Like you have another model training on top of.
That's
Yeah,
right.
yeah.
So if you train a machine learning model, it's very good at smoothing out the noise and extracting the true pattern, and it can outperform the noisy teachers.
Obviously, there's a lot that's been going on in natural language processing the last few years. It's been some incredible leaps. So, what are your thoughts on the current state of natural language processing right now?
I think NLP is definitely a very hot research topic right now in AI.
Mm.
And also, um, it has changed our life. For example, ChatGPT, I use ChatGPT a lot.
Oh, do you? Yeah.
Yes, for example, some, let's say, paper editing
Yeah.
or just getting a better expression,
Mm.
or maybe I have some doubts about a particular point. I just ask a question, but I need to verify it myself.
Mm.
You can't just purely rely on that. And it has greatly changed the research landscape of AI and also NLP because right now we have so many researchers in the field. It's kind of crowded.
Right.
And also, since it's so easy to prompt a large language model, just like converse with a large language model as a human, I think there are a lot of research that focuses on the short-sighted goals. For example, they just try different prompts and then just get some better performance and you publish a paper. I think this is okay, but I definitely also encourage that researchers who will think deep, think of the fundamental problems of um, large language models and try to improve that from an academia point of view.
Yeah. The improvement of large language models has forced people in academia to ask different questions. Like our
Hmm.
contributions will necessarily be different because we don't have the same resources as, these big tech companies.
Yes, that's right. So for me, for example, I focus on the efficient methods.
Uh,
So our approach is more deployable than those big models if your resource is restricted. And it's also doable in our academic setup.
right. Yeah.
So, given as you just said that, I mean, large language models have definitely changed the way a lot of people do things, changed the way a lot of people kind of approach certain tasks. Your work on improving the efficiency on it, if they got more efficient, what changes? What would happen?
Your phone will be smarter,
Mm.
even if it's offline. You don't have the data connection, Wi-Fi access. You can still prompt the phone and get some suggestions for your daily life. That's
Because
an immediate application of efficient models. And I think
it's like right now that they kind of send that information to somewhere to actually do the processing rather
yes,
than
for
actually
high
having
performing models, yes. But for some easy tasks, we can already do that in our phone. For example, if you talk to Siri, set an alarm,
Mhm.
it's pretty much local.
Okay.
And I believe the local model will be smarter and smarter in the future.
It's also, having a local model also solves some problems with security because
Yes.
your data is not leaving your phone.
Yes,
Yeah.
that's right.
Like
Yeah.
maybe that would have a lot of benefit for things with sensitive data like healthcare, stuff like that. Is that something you're exploring?
Yes. So I currently have a project about radiology report analysis,
Oh,
and it's in collaboration with BC, Ontario, and also Alberta. And because of the legal requirement, we have to train the models in the jurisdictions
Oh, okay.
individually. So that's why we are very restricted by the resources that we have in each of the centers.
Right.
And we are indeed applying some distillation techniques so that the model is trainable on a small device.
Okay.
And we are also looking for other techniques, for example, federated learning. So we don't communicate the data. We probably share the parameters because parameters are less sensitive than data. So
Right.
if that is legally allowed, we can share the parameters and we can build a strong model, but the data never leave their jurisdictions. So there's less privacy concerns.
Mhm.
Okay. Wow.
It's a good description of federated learning too.
Yeah.
Yeah. Great job.
So what do you think? Where's NLP research heading in the next 5 to 10 years?
Yeah, I think there are two general directions. One is bigger and bigger, and the other is smaller and smaller.
Huh.
So we definitely acknowledge the performance of super big large language models, and I think the trend will continue. But the other direction, as I mentioned, will be efficient methods to make it smaller and smaller, and it can change our life in all kind of setups.
Wow. That's
Yeah.
interesting. That's kind of going to the both extremes of the spectrum.
Right.
Well, one thing I did want to sort of drill down on was you're saying that you wish people used more theoretical knowledge to inform NLP. So what can you tell us like an example of what you mean by that?
Yeah. So, for example, transformer model, the most widely applied architecture for NLP, is mostly designed by heuristics. So you just build this layer, uh, like a feed-forward layer, and then you have some attention layer to fetch information of the previous words, and then you just move on layer by layer, and it can do a lot of things for you. But we don't understand why.
Mhm.
Why do we have to design the model in such a very particular way?
Mhm.
So some theoretical research, for example, explains the power of a transformer model. For example, they can show that during the in-context learning, just meaning that you just prompt the model, it's doing some kind of gradient descent method. So it's more and more narrowed down to the problem you are looking at, and it gives you better performance. So I think this kind of research, it complements the industrial setup that they are just building the model for better performance. But now we're having a better understanding of why this model works and how can we design a next generation model with some theoretical justifications.
Right. Because you put all these things into the model and it's not completely clear that you need all of it. So maybe figuring out which parts are most
Yes,
necessary.
exactly. So
Yeah.
in that case, we can do some model pruning and model compression, and you can also improve the efficiency.
Yeah. Right. Which you love. You love improving
Yeah.
efficiency.
So in this like a kind of an ever-changing landscape there, during your research, has there been anything that you've worked on that really surprised you or you went in a direction you hadn't expected?
So in our distilling research, we find that matching the intermediate layers of the teacher and student is important. For example, you go step by step, the student learns step by step from the teacher, and it gives you generally better performance. But what we found was uh, the which layer you match doesn't really make a difference.
Mhm.
So that's very
Okay.
surprising. So
Oh,
you have to match the teacher layer by layer,
uh-huh.
but you can even match the reverse order.
Huh.
So that's a surprising finding.
Huh.
And we did more analysis, and we find that the one of the possibility is that the between model distance is much bigger than the between layer distance.
Mm.
So you
Okay.
see the teacher is here, the maybe the student is here, the teacher is here, and it doesn't really matter which layer you are matching. As long as you match the teacher, it gives you a step-by-step guidance, and it gives you better performance during the distillation process.
Mm.
So we did an empirical study showing that the performance really don't change much,
Oh, wow.
even if you reverse the
Reverse.
order.
Yeah.
And we provide some evidence to justify this kind of intuition. And we're submitting a paper about that.
Huh. So
That's
maybe
one of
like the
the,
matching gets you sort of in the right neighborhood,
yes,
right?
that's right.
Yeah.
So as long as you follow the general direction of the teacher, you're good. You don't have to do exactly what the teacher says.
Ah,
Huh.
well, that's a
Yeah.
good lesson to learn.
Yeah, I guess maybe if any school children watching, maybe be careful with that advice. You don't have to listen to exactly what the teacher says step by step.
I thought you
That's
were going to
right.
say kids out there, you do have to listen to your teachers.
Yes,
Well, I mean, that would be
We're
in
great.
the
not
general direction,
Yeah.
yes.
Yeah.
But for the very particular detail,
Right.
maybe it doesn't matter that much.
Yeah. And that's innovation, right? Innovation comes from, listening to people around you, but doing something just a little
Yes.
different. Yeah.
Oh.
Yeah.
And then we did want to ask about Upper Bound because we're kind of coming up on that time of year again.
Yeah.
Can you remind us what you did for last year's Upper Bound and what it was like?
Yeah, so I was the organizer for the large language model track together with Alona and Dell, one of our colleagues.
Mhm.
And we had a rich program on large language models last year. And myself and Alona gave a tutorial about large language models. I think it laid a very good foundation for the general public to understand what LM is
Mhm.
and how it performs in different tasks. And I also gave a talk on the multi-teacher distillation. So it will be more technical than this podcast.
Mhm.
But I think it was well received by the audience. And other speakers also gave fantastic talks, such as the researchers from Google. They talk about the latest techniques in the industrial practice.
Mhm. Yeah, it's one of the things I love about Upper Bound is all of the different people who are there.
Yeah.
Yeah, there are industrial people, there are researchers, faculty members, there are also students. So when you talk to different people, you have the ideas bumping,
Yeah.
and sometimes you get innovations, or sometimes you see applications, and you can spin off some even startups, or you apply your techniques to different sectors of the industry.
Yeah, it does bring together groups of people who might not otherwise be in the same room.
Yeah.
So really cool things can happen.
Yeah, and it's really rare to have that many perspectives and different areas of expertise and experience all kind of one place talking.
Yeah, I'm looking forward to the event.
Yeah, me too. It's always fun.
Yeah. Well, I mean, it was absolutely fantastic to have you here. I learned a lot about large language models and what they do and what they could do in the future. So thank you very much.
Thanks for coming, Lili. It was great to have you.
Thank you for having me here.
You don't want to make a Flora joke?
Yeah.
Okay, sorry.